Hello, my name is Zhen Gao. I come from Beijing Institute of Technology and I am a PhD student at Professor Zhen Gao's group. Then I will introduce a paper published in the IEEE GXTSP recently on behalf of our group. The title is Sensing User Channel and Location with Terahertz Extra-Large Reconfigurable Intelligent Surface under Hybrid Field Beamsquint Effect. The paper mainly focused on how to sense the user channel and location under the hybrid far-near-field Beamsquint effect with the help of anchors. Therein, the wreath is served as an anchor. I will introduce our paper from the following 6 points. The background of the question will be described in the introduction section. A train of thought section will describe how we find the problem and why to solve this problem, and how to solve this problem. Key construction method of signal model will be described in system model section, focusing on how to sense the user channel and location under the hybrid far-near-field Beamsquint effect with the help of anchors. 2 schemes are proposed in proposed scheme section. Our proposed schemes will be verified in the simulation section. Finally, we will conclude the paper and looking forward to the future research direction. In order to satisfy the increasing demand of communication rates, the frequency of communication systems become higher to improve spectral efficiency. The higher frequency, the smaller wavelengths, which make more antenna elements in unit area possible, as can be seen from the relay distance in Figure 1.1 under the condition of the same array aperture. The smaller wavelengths means the larger relay distance, and also means the communication scenario will change from far field to the hybrid far-near field. Moreover, higher frequency is accompanied by great bandwidth. Bandwidth resources are abundant in higher frequency band, which breaks the promise that the bandwidth is far less than the sensor frequency, and the array aperture is comparable to the distance propagated by the electromagnetic wave in the baseband sampling interval. There will exist obvious Beamsquint effect. The consequence of this Beamsquint effect is illustrated vividly in Figure 1.2, where different frequencies will correspond to different angles under the far-field Beamsquint effect, and different locations will be focused by different frequencies under the near-field Beamsquint effect. The coexistence of far-field and near-field makes the channel present the hybrid far-near-field characteristics. Together with the Beamsquint effect, the hybrid field Beamsquint effect arises. However, the deep integration of communication and sensing is a key capability for future communication systems. Therefore, how to sense the user channel and location effectively under the hybrid field Beamsquint effect is a worth challenge. Next, I will introduce our train of thought. We will start with and focus on the problems of the current schemes. The first question is Polar Domain Transformation Dictionary, for short PTM, has been proposed by this paper. It is used to replace the DFT dictionary to estimate the near-field channel. However, the PTM can't work when there exists a Beamsquint effect. To this end, we propose the frequency-selective Polar Domain Redundant Dictionary, for short FSPRD, to solve this problem in the later section. The second question is, in terms of the joint channel estimation and localization, in the case where the channel is known to the cluster but not past terahertz channel, only a single item being selected in each iteration is optimal or not is open to discussion. We expect to learn from this paper to select more than one item to improve the performance in estimating the channel with clustered unlost passes. The third question is under the Terahertz scenario, if the radar cross-section for short RCS of scatters is small, the energy of unlost passes is small and it is difficult to extract useful UE location information. If the RCS of scatters is large, the energy of unlost passes can be increased, but the diffusion problem of angle will become severe, which also makes the extraction of UE location is challenging. Therefore, how to guarantee the existence of the loss link in the terahertz channel is an important thing. Moreover, the PTM proposed by Cunmin Yao in his 2022 paper DCOM has the resolution of the distance. Then it can be used to locate the user. The answer is no. On the one hand, the number of distance grid points divided by it is very limited, which results in the limited distance resolution. On the other hand, due to the influence of large-scale feeding, as can be seen clearly in Figure 2.1, although the true location is at 16.7 meters, the estimated location with maximum energy is at 13.99 meters. Figure 2.1 depicts the inner product of the real channel and the hybrid field steering vector, wherein the left subfigure is in the far field and the right subfigure is in the near field. As can be seen in it, if the Beamsquint effect is ignored, there exists obvious location error. To solve the problem mentioned above, we expect to introduce the wreath as an anchor to locate the UE with multiple angle of levels. In this way, considering the Beamsquint effect and utilizing multiple AOA to locate the UE, it is bound to be more accurate compared to only utilizing the precession limited PTM and ignoring the Beamsquint effect. The question 4 is the channel estimation and localization two separate processes. Can joint process provide some benefit? The answer is that these two processes are not separate, and the joint process can reduce the computation overhead. The question 5 is that if we want to locate the UE estimating the channel, only two AOAs of two lost passes are enough. Then, can we obtain the AOA accurately without estimating the delay? The answer is yes, and we propose the PGD algorithm for this purpose. This figure will be depicted detailedly afterwards. The scheme described previously is the case that the channel and the location are estimated at the same time. In reality, there are definitely situations where only the location needs to be sensed. But can the pilot overhead in estimating the parameters of unlost passes be reduced if only the location needs to be sensed? The answer is yes. We can not only estimate no parameters of unlost passes, but also estimate partial parameters of the lost path to accomplish the location task. The question 7 is, since the delay in the OFDM system is not the absolute value, and is the value relative to the first path, how to locate the UE utilizing the delay of lost path is a problem. Assisted by the wreath, we can lock the UE on the hyperbola by two delays of lost passes. One lost path delay is the one from UE to the BS directly. The other is the one from the UE to the BS via the race. The question 8 is that when the subcarrier spacing is fixed, the larger bandwidth, the more subcarrier can be used. Since the bandwidth is large in Terahertz systems, the data dimension is huge and the computation overhead is also huge. Therefore, we use the subspace analysis method to reduce the computation complexity of the eigenvalue decomposition. Moreover, hierarchical search can be utilized to further reduce the spectrum search complexity. Next, we will introduce the system model from the equation in the paper. This equation describes the uplink channel on the AMS subcarrier. The first summation represents summing the channels of all clusters, where L equals to 0 represents the loss path. The second summation represents summing all passes in one cluster, since L equals to 0 represents the loss path, namely J1 L equals to 1 equals to 1. The third term represents the phase caused by the delay on different subcarrier. The first term represents the channel gain, and the fifth term represents the hybrid field beam steering vector, which is related to frequency, angle, and distance. When the UE is far from the BS, the hybrid field steering vector will degenerate to the far-field steering vector. Also, the boundary between the far field and the near field is the effective relay distance. Compared to the conventional relay distance, there are two main differences between them. One is that the effective relay distance is defined by the origin loss, while the conventional one is defined by the phase differences. The other is that different AOAs have different effective relay distance. This can be understood easily by considering two extreme cases. One is the AOA is 90 degrees relative to the array normal. In this case, it is definitely the far-field case. The other is the angle of travel is 0 degree relative to the array normal. In this case, the near-field spherical wave is the most obvious. After defining the channel model, let's define the received signal model. The received pilot signal from the UE to the BS directly in the peace time slot on the AMS subcarrier is constructed by the transmit pilot signal, the channel between the UE and the BS and the BS combiner. The received pilot signal from UE to the BS via the race in the peak time slot on the AMS subcarrier is constructed by the transmitted pilot signal. The phase matrix of the race, the channel between the UE and the race, the channel between the race and the BS and the BS combiner. Then we stack all the received signal from all the time slots. Since the transmit pilot signal is known, we can remove it in the expression of our received model without loss of generality. Hence, we can obtain the received signal model comprise the known sensing matrix and the unknown channel. Therefore, due to the high path loss of the multi-hop signal in the terahertz band, we model the channel between the BS and the race as a loss channel only. Additionally, since the race is deployed in advance, the channel between the BS and the race is totally known and can be seen as a composition of the sensing matrix. Our goal is to estimate the channel or extract the parameter in the channel, so the received signal Y and sensing matrix W. Now I will introduce two schemes proposed by us to sense the user's channel and location under hybrid field Beamsquint effect. we introduce the overall framework first. The first frame is the joint channel and the location sensing scheme. First, we transmit the uplink head signal to observe the channel. In the CE model, we estimate the channel by invoking the OMP-based algorithm. In the first correlation step of the CE stage, the result can provide a cross initial value for the localization model to conduct further, more precise localization. Then, the localization results of the localization model can be utilized to improve the lost channel reconstruction performance. Compared to the PTM, FSPLD has an additional dimension of subcarrier, namely, different subcarriers have different steering vectors, which will overcome the Beamsquint effect in the channel estimation stage. The framework of the proposed LAP and the OMP algorithm is the classical OMP algorithm. Therein, lines 8 to 12 are the interaction between the channel estimation and the localization. Channel estimation provides an initial value to the localization process in line 9. Invoking the localization algorithm and returning the localization result to the channel estimation process to improve the performance of the reconstruction of the lost channel is shown in line 10. Updating atoms in the final selected detection way is shown in line 13. We are selecting only one atom to reconstruct the lost channel while selecting multiple atoms to reconstruct the unlocked passes. The concrete reason is that as for clusterized channel, if only one atom is selected in one iteration, the energy of other atoms with a similar angle or distance value will be weakened. Therefore, this atom will hardly be selected in the subsequent iterations. However, if multiple appropriate atoms are selected, the reconstruction performance of the unlocked passes will be improved. The adaptive iteration stop criteria in line 19 is different from the conventional residual-based criteria, which can bring much stable channel estimation performance. As for AOA of the loss path from UE to the BS, how can we estimate it accurately without estimating the distance? The answer is to design the loss function subtly. If we adopt the conventional loss function, we can visualize it and say that if the distance is not accurate, the angle can't be estimated accurately. However, if we adopt the loss function designed by us, namely the green box, the AOA estimation will no longer influenced by the unknown distance. The essential idea behind this is to eliminate this term in the channel model. You can go to the previous section to recall this term in the channel model. If we can eliminate this term perfectly, the AOA estimation can be no longer influenced by the unknown distance. First, we design the combiner shown in the blue box. Then, we perform the operation in the pink box on the received signal. Finally, we generate the channel with only the steering vector. The phase term, this term, corresponding to the distance is no longer generated. Through these three processes can we change the loss function shown in the left subfigure to the right subfigure. Next, Armstrong-Goldstein criterion can be utilized to conduct gradient descent algorithm and obtain the accurate AOA estimation. It was noted that in the blue box, we only observe the phase of center elements of the array in one of all time slots and in one of all the RF chains. In fact, we can observe the phase of center elements of the array in any time slot and any RF chain so as to realize in-phase superposition, which can reduce the effect of noise. However, it is not so fortunate to estimate the AOA from UE to the race. The essence behind it is that the sensing matrix used to estimate the AOA from the UE to the BS is independent of frequency, while the sensing matrix used to estimate the AOA from UE to the BS is dependent of frequency. Therefore, we can't remove the phase term corresponding to the distance to in PhD. We can take the second best choice. We estimate the AOA from the UE to the RIS using the hierarchical correlation method, wherein the hierarchical diction used is called the polar domain hierarchical dictionary, for short PhD. After introducing the joint channel and the location sense scheme, we introduce the location sense scheme without channel estimation. Similarly, we first transmit the uplink spectral signal to observe the channel. Then, the delay difference between the one from the UE to the BS and the one from the UE to the RIS is obtained to lock the UE on the hyperbola. Next, we generate some FSPRD on the hyperbola to lock the UE on grid. Finally, we invoke the PGD algorithm to obtain more accurate UE location. The UE is locked on the hyperbola and the final location is estimated by the additional half of the AOA from the UE to the BS, is graphically presented in the left figure. Just like I introduced before, the delay of the loss path doesn't represent the true delay from UE to the BS directly or from the UE to the BS via the RIS. Therefore, we obtain the delay differences of two loss paths to obtain the time difference of variable, where the common time offset can be eliminated by the process of subtraction. Since the loss paths play a leading role, the dimension of the noise space is known. Therefore, we can learn from this paper to avoid eigenvalue decomposition and only use the subspace analysis to obtain the noise subspace. Finally, we can obtain the TDOA by the hierarchical spectrum search. The final UE location is obtained invoking the previous PGD algorithm. Now, we introduce the simulation results, which will verify the superiority of what we mentioned previously. Let's look at the estimation performance of the channel from the UE to the BS. GL represents the number of paths in the cluster. This one. NS represents the number of atoms selected in each iteration. This one. First, through the comparison between JL equals 1 and JL equals 6, we can find that the estimation performance of the channel without cluster is better than that of the channel with clusters. And for the channels with clusters, namely JL equals to 6, selecting multiple atoms in each iteration can bring remarkable improvement, and the performance platform is not obvious compared to the NS equals to 1. The performance of channel estimation assisted by location is better than the one without assistance of the location obviously. In estimating the channel from the UE to the RIS, due to the poor property of the condition number of the sensing matrix, Gini LS will over-amplify the noise. The consequence is that the proposed algorithms can surpass the so-called lower bound. As for channel estimation performance, it is better to design the combiner using 13 than using equation 13 than equation 12. Since the energy in different frequencies is more balanced when equation 13 is adopted, if equation 12 is adopted, the energy in the center frequency is higher, while the energy of the marginal frequency is lower. However, if we locate the UE using the time difference of variable, adopting equation 12 is better than adopting equation 13. The reason will be explained later. These figures show that the localization performance versus the transmit power. It can be seen that as far as the AOA localization performance, the CDL and the PDL scheme are the best. As far as the distant localization performance, the CDL scheme and the GMMVOMP algorithm is the best. Then, the CDL scheme represents the joint channel and location sensing scheme, while the PDL represents the location sensing scheme without channel estimation. Due to the effect of the Beamsquint effect and the near-field channel, the subspace-based algorithm performs very poor. Figure 5.4 illustrates that the main factors of the poor performance of the subspace-based method are the Beamsquint effect and the near-field channel. From the comparison between bandwidth equals to 500 MHz and the case where bandwidth equals to 10 GHz case, we can see that the influence of the Beamsquint effect on localization performance is decisive. From the circled curve, we can see that the AOA estimation accuracy of the far-field case is higher than the near-field one. The SNR of the far-field case is lower than the near-field case when the transmit power is the same, which illustrates that the near-field channel is also a factor that leads to the localization performance loss of the subspace-based algorithms. We simulate the CDF performance of the different localization algorithms in Figure 5.5, from which we can see that the proposed algorithms perform better than the baselines. No matter whether the combiner is designed according to equation 20 or equation 13, 12 or equation 13, it will not affect the localization performance of CDL. However, for the PDL scheme, using equation 12 can achieve better distance localization accuracy. The reason is that only the phase difference among different subcarriers of the channel is considered, but the phase difference influenced by the sensing matrix is not considered in using the music-based algorithm. Therefore, we can conclude that for channel estimation or joint channel estimation and location sensing scheme, we can design the combiner based on equation 13. For sensing scheme, not relying on channel estimation scheme, we can design the combiner based on equation 12. Finally, I will summarize today's paper presentation in a nutshell. In our paper, in order to solve the problem that the PTM can't work well under the Beamsquint effect, we propose the frequency selective pro-domain redundant dictionary FSPRD. We design two localization paradigms depending on whether the channel is needed to be estimated. The scheme for joint channel estimation and location is called CDL scheme, and the scheme for location sensing not relying on channel estimation is called PDL scheme. We verify the effectiveness of the proposed scheme by the simulation. In the process of the formation of the scheme, we have found that some new problems need to be fixed in the future. They are more reasonable beam training procedure instead of designing the combiner omnidirectionally so as to increase the received SNR. More reasonable design of the race phase instead of assigning random phase in order to increase the received SNR. That's all my presentation. Thanks.